All right, I'm going to show you three examples on implicit differentiation, which is a fancy way of doing derivatives. Here's an easy way of doing derivatives. Before I show you the fancy way, let me explain the easy way. The easy way is normally you have an equation where y equals something in terms of x. And then you could just take the derivative by using the power rule. The exponent times the coefficient, and you subtract 1 from the exponent, and you get 6x. 3x squared becomes 6x when you take the derivative. But what happened to the y? You kind of took the derivative of y also. The derivative of y is just 1, just like the derivative of x would just be 1. If we were trying to take the derivative of x is really the coefficient of 1 and the exponent of 1. 1x times 1x to the first power. So it'd be 1 times 1 if we were going to take the derivative, which is 1. And then subtract 1 from the exponent to get 0, and anything to the 0 power is 1. So it'd be like 1 times 1, which is just 1. So if you're ever wondering why the derivative of x is just 1, it's just the power rule. Well, the derivative of y is the same way, but whenever we take the derivative of y, we kind of leave a mark that we took the derivative of y. So the derivative of y is like 1 derivative of y. It's kind of weird, but that's what you do. So you really took the derivative of both sides. All this time you've been doing the power rule, it seems like you're only taking the derivative of x, but you're really taking the derivative of y, and we just leave the mark that that's what that means. We took the derivative of y. So now implicit differentiation is when the problem is not already solved for y. It's not, you don't have y equals everything over here. You've got y jumbled in with the whole equation. So now we're going to take the derivative of x and y, but whenever we take the derivative of y, we're going to leave a y derivative symbol. So we're going to take the derivative of all three of these terms, just like we took the derivative of both of these, and whenever we take the derivative of y, we just leave y to the little prime mark there. Okay, so the derivative of 3x squared is 6x. The derivative of 4y squared is 8y, but we took the derivative of a y, so we got to have the y derivative. And the derivative of a constant is 0. Now we just solve the problem for the y prime, the derivative of y. So that means we have to get the 6x term to the other side, so we subtract it to the other side. And then we have to get the 8y to the other side, and it's being multiplied by the y prime, so we divide it to the other side. And then we simplify it, we just reduce our fraction, and we're done. That's the answer. So that's the whole gist of implicit differentiation, is you're taking the derivative of x and y, and once you take the derivative of y, it leaves you with the y prime, and then you just get y prime by itself. Then you just solve for y prime. So let me show you another example of that. Here's an equation, xy plus 12. So we're going to take the derivative of xy, but now we have to use the chain rule because we have two terms being multiplied together, x times y. So the chain rule says when you multiply two things together, like a times b, you take the derivative of the first one, a, just times the regular old second one. You don't change the second one. And then plus the derivative of the second one times the regular old first one. You don't change the first one. So that's what we're going to do here. The derivative of the first one, derivative of x, is just 1, and we don't change the y, so we end up with 1y. Plus the derivative of the second one, derivative of y is 1, but remember, whenever we take the derivative of y, we leave a y prime. So it's like 1y prime, but I don't write the 1 there. Times just the regular old first one, the a, the first term. So this is the chain rule for x times y. And then the derivative of a constant is 0, so that's gone. And then you solve for y prime. So you subtract the y to the other side, that's where that negative y comes from. And then you divide by the x. So that's what you get, negative y over x. All right, one more, and this one is ugly. It has lots of terms, chain rule included. So 3 terms over here. Technically there's 4, but that's just going to turn into 0. So let's start taking the derivative of these 3 terms. First one's easy. 4 times 2 is 8. Subtract 1, you get 3 exponents. So 8x to the third. Now we have to use the chain rule for this. So the derivative of the first one is 2x. Don't change the second one. Plus the derivative of the second one, that's 2y. And we took the derivative of a y, so we got to put the y prime in there. And then you don't change the first one. X squared stays x squared. So this whole thing from 2x all the way to x squared is the chain rule of x squared y squared. Plus the derivative of this, which is 4y to the third, and we took the derivative of y, so we got another y prime, and the right-hand side turns into 0. Okay, now we get into some crazy algebra. We got to solve for just a single y prime, but we have 2 y primes, so we're going to factor out a y prime from our second 2 terms here. So I'm going to put parentheses around those. So I just added parentheses around these 2 terms. So it's this whole crazy term plus this that each have a y prime in it. So I'm going to pull a y prime out. That's what this is. And then what's left is 2yx squared in the first one. That's this. And what's left over here is just a 4y to the third. That's this. And then these 2 terms, we could just subtract them to the other side, because eventually we want y prime all by itself. So let's just get rid of these. Let's subtract the 8x cubed to the other side, and let's subtract the 2x y squared to the other side. So that's where that comes from. Now y prime times all this, that means we got to divide this whole parenthesis to the other side. So that's what this next line is, which I guess I kind of skipped a little bit here because I factored it at the same time. So before we divide that to the other side, let's factor this numerator. In the numerator, you have a 2x in both terms. That's the greatest common factor. You could pull a 2 out of this and an x, and you're left with negative 4x squared. So I rearranged the order. It's because this is taken from a multiple choice question on a test, and they rearranged it for some reason, so I'm rearranging it. I'm putting the negative x to the third as the second term here. You pull out a 2x here, and all you're left with is a negative y squared. So that's this. And I pulled out the 2x. Okay, now I drop this down to the denominator. I divide that to the other side, and I factored it all in one move. Sorry about that. I usually like to show that as 2 different moves. But to factor this, sorry about the glare as well. All right, to factor this, you have a 2y in each term this time. So you can pull out the 2y, and you're just left with an x squared on the first one. Pull out the 2y here, and you're left with 2y squared. So that's how this comes to be. All right, now you can cancel out your 2's. And the final answer on this particular problem, I can't explain why they did this, but they left the denominator alone, which is nice. It's the same denominator as here. But for some reason, they multiplied the x back through. So I don't know why they factor out the y and not the x, but that's what they did. So you multiply the x back in, and you get negative xy squared, which is this. So they rearranged it again. So instead of the negative y squared being the first term, now it's the second term. And then the x times the negative 4x squared becomes negative 4x to the third. And that was the answer. That was the correct answer. And that's how you get there. I'm sorry, I don't know why they didn't leave the x out in front like they did the y. But they did not. And I don't know why they decide to switch the terms sometimes. But they do. So that one is not easy, especially when it's multiple choice, because really you could have left it like this when she canceled out the 2's, and that would have been a perfectly fine answer. But when you look for the choice on the test, you're going to see this, and you're like, that doesn't look like that. But this really is that. So that's why that one's so tricky and not quite fair. But regardless, those are pretty good examples on how you do implicit differentiation. So hopefully that helps.